And this is the Particle Homework Booklet question 29. We're told that when an ultraviolet light of frequency 3 times 10 to the 15 is incident on the surface of the metal, electrons of maximum kinetic energy, that value, are emitted. First of all, we've got to explain why the emitted electrons have got a range of kinetic energies up to a maximum. So we've got some similar ideas to what we've got going on in 30. We've got, first of all, it's worth saying that we've got a fixed energy for each photon, or the energy given to each electron is fixed. That's HF, and so that's linking up to that frequency there. We've got a fixed amount of energy required to leave from the surface. That's the idea of the work function, the minimum energy to leave. You can think of that as the energy needed to leave from the surface. So the maximum kinetic energy would be the energy that the electron gains from the photon, HF, take away the energy, the work function, the energy needed to leave from the surface. You'll notice there that's got embedded in it the idea that one electron is getting all its energy from one photon, one-to-one interaction between photons and electrons. And then why a range up to that maximum? Because electrons which are deeper in the metal surface will require more energy. One thing that's worth noting there, they didn't want to hear about energy levels. Energy levels really referring to isolated atoms, molecules, not a relevant concept when we're looking at metals with their delocalized conducting electrons. And those are the electrons that are leaving from the metal when we're looking at the photoelectric effect. We're asked to show that the work function of the metal is about 1.8 electron volts. So on the surface of it, that's very simple. We've got the equation HF is phi plus EK max. H is just Planck's constant. It's there on your data sheet. Phi is what we're after, the work function, and the maximum kinetic energy we've been given. So there you go, very nice and simple. Rearrange that. Phi is HF minus EK max, just taking EK max from each side. Work out HF, take off that EK max, and there's the answer. And that's where some people stopped, got you 2 marks. It was a show question, so first of all, notice I've been very, very clear what I'm doing at each stage. I've stated the equation, I've rearranged it before substituting and then getting to a value. But I've got to show that it's 1.8 electron volts, and that's not what I've got. But the key here is you've got to remember how you convert from joules to electron volts, simply taking that value and dividing by the 1.6 times 10 to the minus 19. It says 1.8 in electron volts. Part 2, we're asked to calculate the threshold frequency of the material, of the metal, giving your answers to an appropriate number of significant figures. Again, key here is this equation. It does the work for us all the time, but there's a special significance here, which we're at the threshold. We're looking for the threshold frequency. That is the frequency that's just enough to release electrons. And the point is, if we've just got enough photon energy to release the electrons, there won't be any kinetic energy. So at the point where the frequency is the threshold frequency, phi, the work function, is equal to HF naught. So F naught is phi over H. This now needs to be in joules, which you could either get if you'd worked it out as an intermediate step in the previous point, or if you were relying on the show value, hadn't been able to do part 1, you'd need to convert that into joules. But we need in joules here. Divide that by Planck's constant, and we end up with 4.3 times 10 to the 14. Give your answer to an appropriate number of significant figures. Why am I giving that to 2 significant figures rather than 3? Because we've, right at the top, the maximum kinetic energy was only given to 1.7 to 2 significant figures, and that maximum kinetic energy, if I can get hold of this, that maximum kinetic energy was used to work out the work function, and therefore this value, although I've written down 3 significant figures, that's only good to 2 significant figures. I left it in 3 because it was an intermediate stage, and therefore when I then use that value on here, I can only give my answer to 2 significant figures. This is just a little note here that we've got to use the work function in joules, not in electron volts. That is a standalone mark for any answer to 2 significant figures there for the 3rd mark. We're asked then to state and explain the effect of the emitted electrons on the emitted electrons of decreasing the frequency. Unfortunately, there are 4 possible answers to that, and I've tried to put those in terms of stating and explaining. If I decrease, the most obvious perhaps, if I decrease the photon energy, that's going to decrease the maximum kinetic energy of the electrons. An extreme version of that is if I go below the threshold frequency, I'm going to get no electrons emitted at all. Any of these 2 pairs are good for the 2 marks. Another possibility, if I decrease the photon energy, I'm going to get fewer of the deeper electrons escaping. So actually the rate of electron release will be lower. And here's the really subtle one, which is quite clever and gives us a counterintuitive answer. We're told that the intensity is constant. If my photon energy goes down so the energy of each photon goes down, but the total energy arriving each second, which is essentially what the intensity is here, remains the same. That's the total energy arriving each second divided by the area. That must mean I've got more photons arriving per second, so I could have more electrons escaping. So as long as you could match an explanation to a statement, you could have those 2 marks, even if we've got contradictory ideas going on with fewer electrons escaping or more electrons escaping. Best of these should all be per second, fewer electrons per second. It's all about rate. The actual number you get will depend on the time as well. We'll focus on that point. Again, in this very last point, we're asked to state and explain the effect of the emitted electrons of doubling the intensity. Often, and I did it above as well, but it's actually easier to do the explaining before stating what that then means. If I double the intensity, I'm doubling the rate that photons are arriving at. If I'm doubling the rate that photons are arriving at, that should double the rate that electrons escape. So if I double the intensity, in fact, I will double the current leaving from the surface. So that's the Particles Homework Booklet, question 29.